There we go. Well, since we have a few minutes, before we start the class, um, let me just see what you guys think of going back on campus. Because ARC is making an effort to try to encourage professors like myself to get back on campus. In other words, they would prefer to offer classes on campus again in the fall. So, what do you guys think? Do you guys prefer to take classes on campus, or do you want to kind of stay online? Yeah, the new building is nice. The classrooms are very nice as well. I know math is a lot of the math professors are getting back on campus already, so I know some of you are already, um, you know, getting into those newer, classrooms. And my office is going to be nice too. I see. Okay, okay. And also, there are people who are looking into a hybrid between on campus and also online. Um, so that's going to be an interesting one. Yeah, I think computer science classes are in many ways like math classes too. Where a face-to-face class can be helpful in terms of being able to ask questions directly and get an answer in right away. Um, Maybe the math notation part is a little bit different because I'm fairly familiar with math notations, but not everybody um, is familiar with LaTeX. Well, besides, I have a nice office. My office is on the third floor of the STEM building, and it has a window. So, I have really good reasons to kind of get back on campus. It's a so okay. Before someone says, "Well, are you getting a nice office because you're department chair and you're giving yourself the privileges?" No, no. The window office is double occupancy, so you get a little, you lose a little because in terms of square feet per person, a double occupancy office has less square footage per person, and you'll be sharing with somebody else. So someone who likes to kind of values privacy a whole lot, may not like a double occupancy. Yes, we do. Well, not exam two. We have the second part two of exam one. So we're gonna reboot exam one. That's settled on Pi Day. Exam two, I have not set the date yet. So that's gonna be yeah, I haven't decided yet. Usually, you have at least a week before the exam, right? I mean, because I give you a practice test first. So there's that. I think I want to finish propositional calculus before the next exam. So we are at least I would say a week and a half off. Easily at least another week and a half before we can have the practice test, and then 1 week after the practice test, we get the actual test. So. Oh, so the other thing about going back on campus is one of the reasons why I'm going back on campus is to have face-to-face exams. So that kind of goes back to the question of people who do not want to be on campus because once I get back on campus, all the exams will be proctored face to face. So it might be certain people may not want to take those classes because it's going to be all face to face. It kind of all depends on whether the vaccination requirement is still going to be there or not because we are technically in an endemic, not a pandemic anymore. So there's also that. A lot of things can change between now and end of August, right? So we don't know. Nobody knows. Maybe World War III will break out and we don't have a single thing to worry about. And the virus will be gone too, because there will be no host left for the virus to invade. Yes, sort of. So Vlad makes an interesting point. So I am trying to make my test so that proctoring is not really needed. Basically, people who want to try to copy answers, they're not gonna. It's not gonna work, right? But yes, there is that point. I think that's what's driving most of the math professors to get back on campus, is because of rampant cheating. Starting with the beginning of the pandemic. So there is that. All right. Well, it is 12:01, so I am going to get started with the announcements. So the first one is the makeup exam, which is exam one part due or rebooted. Okay, reloaded is going to be next Monday, which is Pi Day. It's going to have the same scope as the exam that you took, not necessarily the same format as the previous one. So there's that. Oh, two is not bad, Nathan. I think some of the STEM professors reported like 200% increase of cases of cheating, and they basically it's like 1/3 of a class or something like that. It's insane. Um, all right, so that's the first point. And are there any questions about the make-up exam for exam one? So once again, I'm gonna write it down here just so that it's written. Okay, so I will take the higher score of the original exam one versus the make-up exam. So that way, if people do not want to, oh, okay, it's not appearing. Dang it. Okay, give me a second. Excuse my language. Yeah, sometimes the server stops working for some reason, but I have not isolated yet why the server would stop working. So what I type is not refreshed on the screen. Yeah, right. Yep. And the interesting thing is online teaching. Getting back to Luke's point, online teaching is nothing new. Okay, the ARC has been doing this for I would say at least 15 years. The STEM area was one of the last area to get online. So humanities like psychology, history, English, those classes have been online for a while, and yet we do not see a whole lot of reports of cases of cheating. And as soon as STEM gets on, the STEM professors are going like, I have no idea why you guys never detected anything. We are seeing these cases left and right. So I'm gonna leave the explanation to you guys to think of why that is the case. And then the next one is I did make a correction to module 20297. I'll show it to you later, but it's also in the Discord text channel at the very top. So if you want to just kind of, if you have made a copy, like printed copy already, and you just want to mark it, there's a explanation of that error in the text channel already. All right, so what we're going to do today is a continuation of the propositional calculus topic. So unless there are other questions that I need to address, we are going to go ahead and resume our discussion of propositional calculus at this point. So I'm just going through the text channel and see if there are any questions right now, and I am not seeing any. All right. All right, so since there are no questions, we are going to move ahead. All right, first thing first. After last Wednesday, I did a few changes to the text, to the module. So instead of having one really long paragraph with a lot of math symbols and whatnot, without any English explanation, I changed it so that it is now at least in bullet points and in parentheses, there are certain English sentences to try to help explain what each one is about. Okay, so this one is not corrected yet. Okay, I want to point out that this is not corrected yet. So you can see there exists a t in omega that is erroneous. Okay, that omega should have been zeta. So that should have been a Z instead of a uppercase omega here. Now that is already changed, so I'm going to do a Control Shift R to refresh the browser. And after the refresh, get back to here, and voila! Now it is fixed. So thanks to Luke, you pointed out, that I used the wrong set, for the membership of T. Now it is fixed. All right, no questions. All right, so if there are no questions, I'm just gonna move on. So don't hesitate to ask questions, when you are not really sure what I'm talking about, or if you think what I'm saying is wrong, because sometimes, I'm careless. I just say the wrong thing. All right, so we're going to go back to the if here. So obviously this is a rule, application of a rule. If all of these requirements are met, then we quote unquote fire the rule, which is to basically perform the quote unquote transformation, and we are going to label another well-formed formula as quote unquote true. Okay, or we just simply say it is derivable. Okay, so remember at the end of the lecture last Wednesday, I said, well, to say something is known to be true is it's kind of it collides with some of the terms that we kind of need to use also. So if we, instead of saying it is known to be true, if we just say that it is derivable from iota, that's a whole lot more context correct and also precise. So that's going to be the term that I will try to switch to, is to say, okay, is this well-formed formula derivable from iota? That's going to be the term. All right, so getting back to the conditional statement, we actually started to talk about this at the end of the previous lecture, but I'm going to get back to this one because I think it is important for everybody to understand what is an element in Zeta. Okay, what does it do? Okay, what is it? What does it look like? What does it do? And how do we use it? So A, B, and C are in W, and W is already defined up here somewhere, and W is basically the set of all the well-formed formulae with respect to the alpha and the omega that we have chosen for this specific propositional calculus system. So some people may say, oh, I really want to use, P, Q, R, S, T, U, V in as the English letters in alphabet. So be it. Okay, you can have more, you can have less. It's okay either way. Or some people may say, I think we don't really need implication, nor do we need if and only if or equivalence, because those can be derived using just the three that we know already, which is negation, conjunction, and disjunction. So be it. Okay, so you can change your omega a little bit if you want to, to get rid of the redundant or unnecessary operators. And yet someone may say, but Tech, you taught CISP440, and you have taught us that NAND by itself is sufficient to basically spin off all of the other operators. So we can just have one single NAND, which is negated AND operator in our omega, and be done with it. I go like, okay, fine. If that's the calculus system you want to work with, that's the calculus system that you can use. Okay. So no matter what you do, okay, this is just, this W here is relative to the alpha and omega that you have chosen for this specific system. So technically speaking, I really should say this is W and then in open parentheses, alpha and then comma and then omega to make it, quote unquote, a function. But I'm too lazy to do that. Okay, it's just that, okay, let's just make it understood that this W here, uppercase W as a set of all the well-formed formulae, is specific to whatever alpha and omega you have chosen for your system. So do we have any questions about the W itself, what it is, and why it is specific to the set of the alpha and also the set that we know as omega? No. Well, no. It's not a function, but it does depend on alpha and omega. In other words, I don't have a closed form of that function for you. I can algorithmically speaking, I can tell you how to generate all the well-formed formulae, but it's going to be an infinite number of elements anyway. So it's just kind of like, we'll just say that W is a set of all the well-formed formulae with respect to alpha and omega. Does everybody understand that term? The phrase or the way I use that phrase here, with respect to. Which in a lot of proofs typically would be abbreviated as WRT. All right, we got a bunch of people typing. No, not randomly. You have to make it reflect, the kind of logic that you want to apply. So it's not exactly random. Correct. So syntactically correct expressions is what W is about, and it is contained or constrained by the valid combination of alpha and omega. Yes. But just keep in mind that your alpha doesn't have to be just have PQRST as the English letters or English alphabet letters. You can have just PQR if you want to. You can have PQRST. You can have PQRSTUV. It's just how many variables are we dealing with here? But your W is dependent on how you choose your alpha and how you choose your omega. Okay, so getting to D. Okay, so we're going to get to D next. Okay, so that's a good question, Danny. All right, so next is we choose a T, an element T of zeta. So T is a transformation rule because zeta is a set of transformation rules. So that makes T a member, which means it is a single transformation rule. And then the third point here is to say, okay, what does T look like? What does a transformation rule look like? Well, a transformation rule has two parts. Okay, this is the left-hand side, which is uppercase M, and then we have this symbol here, which is in first. But if you want to type it in LaTeX, it is \V dash. It's just a separator. That's all it. Or that's syntactically that's all it does is to separate the first portion from the second portion. And then the second portion it needs a little bit of explanation. It's WFFQ, and then in parentheses we got our three Greek letters, which is theta, phi, and psi. All right, so M is a set. Okay, so we'll explain that later on. What is WFFQ of theta, phi, and psi? That's basically is just a notation. That all that is a notation to say, okay, let me answer Danny's question. It's that. All right, so WFFQ is really just a representation of a well-formed formula. Okay, it can involve conjunction, it can involve disjunction, it can involve implication. It's just a well-formed formula. Okay, it has a certain structure to it. And then in the well-formed formula, it can refer to the Greek letters. Now I have chosen only these three Greek letters here because it's consistent with the alpha that I have been using. Okay, in the alpha that I have been using, I've only used these three Greek letters in alpha. So whatever number of Greek letters you have in your alpha, you kind of have to name them all inside the parentheses. So all this is saying is we have a well-formed formula where other than the operators, all of the terms in the well-formed formula will refer to these Greek letters. Now it doesn't force every single one of these Greek letters to be actually mentioned, but we have this set of Greek letters to choose from when we want to stuff the content of this well-formed formula. So is that okay? Is that clear what WFFQ is representing? It's just representing a well-formed formula that is in W, and in the well-formed formula, it only mentions the Greek letters. It can mention all three. It can mention a subset of these three Greek letters. And that's the concept of WFFQ of theta, phi, and psi. So I'm going to pause until people tell me that this is all okay and we are ready to move on. All right. Would these three Greek letters possibly stand for two operands and an operator? They can only be operands, they cannot be operators. The Greek letters are basically placeholders for values. Oh, I just pressed the key and it jumped to a different location. So let me get back to where we were. There we go. Okay, next question is the Greek letters are from alpha. Yes, that is the case. All right. Okay, cool. Most of the examples we have seen just use two. There will be some that will use three. Specifically, resolution, which I hope we can get to today, is a funny looking rule, but it uses three Greek letters. So we'll get to that one, hopefully. W is the superset of D. Okay, so if you look at it this way, your D is a subset of W. But we haven't really quite described what is D yet. Okay, so that's going to be the next item. So right now we just want to focus on the notation of what is W, F, F, Q, theta, phi, and psi. But then it is correct. We're going to use W to help us define what D is. M and D are okay. So it looks like we are ready to move on because all of these questions are forward to where we are in the notes at this point. So let's go ahead and move forward. So moving forward, we have this kind of notation here, which is awfully super duper kind of confusing. Okay, so let's just focus on this one. Okay, this one says for all WFF theta phi psi in M. Okay, so let's pause right there. Okay, what is it saying? So how do you parse something like that? Okay, because I think one of the difficulty or challenges of this class is the notation. Okay, how do we parse and read notations like this? So the way I start is to start with the operators. So I start with this operator, which is an element of, right? This is element of, or yeah, this is element of. So we are basically now we're saying, okay, so element of can only be applicable when the right hand side is a set and then the left hand side is a thing that may live in that particular set. So that's the only time where element of is going to apply. So we look at the right hand side first and say, okay, what is the set that we are talking about? Well, the set that we're talking about is M, which is the first part of a transformation rule. So if you take any transformation rule out of Zeta, the first item, which is the one to the left hand side of the V dash or the inverse symbol, is a set. Okay, so we got it. Okay, it is a set, which means it can have members. Okay, next. It can have potential members. So what kind of members are we looking at? They're all well-formed formulae. Okay, when we see WFF, it means well-formed formulae. But not only is each element a well-formed formula, but they also make use of the Greek symbols. Okay, we have the same Greek symbols here. We have theta, we have phi, and then we have psi. So each element of M is by itself a well-formed formula using theta, phi, and psi as the values. But the structure itself is dictated by how the operators are structured. But when it's time to refer to values, so that the operators can operate on the values, all the values will be specified by the Greek letters. Now I only have these three because I only put these three into alpha to begin with. But if you have a bunch of Greek letters, then you have to expand this to include all of the Greek letters. All right. All right. So let me get back to Eric's question. Are M and D related? Sort of, but not exactly. M is a set of well-formed formulae, but those well-formed formulae or formulas can only use the Greek letters. Okay, they cannot use the English alphabet letters. So now the question is, what about this thing here? Because we have a quantified expression here, and what expression? The quantification is right here. The quantification is for all WFF in parentheses theta phi psi in M. That's our quantification. Now, what is the actual expression that we're trying to use here? The expression that we're trying to say, we want this to be true. Okay, we want this to be true is WFF, which refers to the same well-formed formula. But this is not a typo. Okay, it's not. This is supposed to be A, B, and C, which is not one of the English letters that we have used in alpha. Okay, these A, B, and C's, they come from here. So when we say there exist A, B, C, as elements of W, that is what this A and B and C are referring to. So A, B, and C are in W already. Okay, they are well-formed formulae that we have constructed out of the alpha and the omega that we have chosen. So now the question is, then what happens to the theta, phi, and psi, and how do they relate to A, B, and C? Look at it this way. This is how you call a function. These are the arguments. This is the prototype of a function. So how you name your arguments, when you're defining a function, does not have anything to do with what values you can pass when you need to call a function. So I hope that analogy works, because I just thought of it. I just go like, okay, so what is a concept that you guys already know about that kind of explain what I'm trying to do here? Function, okay, your function calling. This is a function prototype. We just basically say, okay, this particular well-formed formula, we can look at that as a function that has a single return statement, right? So this particular function that returns a Boolean has 3 parameters. The name of the parameters are theta, phi, and psi respectively. And then the return value is obviously going to be hopefully some complicated Boolean expression using conjunction, disjunction, negation, and references to these names of parameters. But here we are applying the function. We are basically saying, okay, remember these A, B, and C? A is a well-formed formula, B is a well-formed formula, and C is also a well-formed formula. Pass those specific well-formed formulae as arguments to WFF as a function. So this expands WFF, whatever this thing is defined to be, it's going to expand it and make use of whatever well-formed formula A, B, and C are representing. And once it is expanded, we want that expanded version to be an element of D. Okay, so questions. I can see people are typing already, which is a good sign. Well, it's a good and bad sign, but I'm gonna say it's a good sign. It's a bad sign because it means I'm not explaining things well enough that you guys have questions. But it's a good sign that you guys realize that you have questions and you're asking. So, all right. So for example, A, B, and C could be numbers that are in W. Yes, absolutely. Whereas the Greek letters are placeholders for those numbers. The Greek letters are really just names of your parameters. When you define the function, this is when you call the function. So what value you use to call the function, or the names of the things that are involved when you call a function, has absolutely nothing to do with how you name the parameters. Arguments, yes. So A, B, and C are representing arguments. The Greek letters theta, phi, and psi are representing parameters. So obviously I'm splitting hair, but it is necessary in this case. So I should probably first ask, does everybody understand what is a parameter versus what an argument is? So I'm just gonna pause here a little bit until I get a response from the class. Because those two terms sometimes, okay, depend on who's teaching CISP440, sometimes those two terms are used interchangeably when they are not supposed to be interchangeable. Oh, let's see. I suppose it's a good time to take roll. Let's do that as a break. Okay. So after the break, I'm going to fully explain, what might be an element here, in M, and we have some examples later on too. Okay, so we actually got some examples later on, but we can move things around a little bit and present the examples. All right. Yeah, I almost forgot to take row, which is right here. And the time that I set is already passed, so I'm gonna have to change the time first. So you can see it's already past that time. So I'll give you guys a little bit more time, and let's make it 45. I think that should be plenty of time. I really am not expecting people to say, but I stepped away and I missed the time to take roll. Really? In the like 15 minutes? All right, so I have to give you the word as well, right? So the word is resolution, and let's not type it, okay? Let's copy and paste it. All right, so here is the answer, which is resolution. I'm gonna copy and paste it here, and then we can save and publish. There we go. So the time right now is 12:27, and people have until 12:45 to submit resolution. Just copy and paste. All right, I'm not seeing any complaints that the activity is not released correctly. Sometimes I make mistakes and maybe it's not on the wrong day or something like that, but not today. All right. Okay, so I'm assuming most people are now done with the row taking activity. So yeah, just kind of think of that as a short break, okay? And so now we can kind of get back to our example here. Okay. So I just got a really long text from one of the interns in the Design Hub. It just covered up like a good portion of my screen. All right, so we're going to use an example here. Okay, so we are going to use an example. There we go. All right, so we'll first define alpha. And alpha in this case is going to be the usual, okay, 0, 1, 0, 1, P, Q, R, S, T, and then we got the Greek letters, right? So we're gonna have theta, we're gonna have phi, and then we're gonna have psi. So nothing out of the ordinary, okay, all the usual stuff. And then omega, this time I'm not going to separate into omega 1 versus omega 2 because, I think last time we did that. So this time we're just going to reuse basically the same stuff. So we got negation, we got disjunction, we got conjunction, we got implication, and then we also got equivalence, which is also if and only if. So left, right arrow, like so. Alright, so now we have alpha, we got omega, so we can kind of show some examples of what is going to be in our W, right? So we can say, oh, just pick anything from alpha except for the Greek letters, okay? So the Greek letters are kind of weird, where they can only be used when you're specifying a rule, but otherwise you cannot use those in a well-formed formula. Okay, so kind of a special thing for those things. So we can say, 1 is in W because 1 is a symbol that we can find in what's that? We can find in alpha. There we go. So we can also have something that's kind of complicated and kind of senseless, right? So we can say P and P. Oops. P and P and P, close, close. It's also in W. Yes, it really just boils down to P, right? Once we understand what is conjunction. But from the perspective of is it syntactically correct? Yeah, this is syntactically correct. But you didn't really have to say and P all this time, but it doesn't mean it's wrong, okay? So we can definitely do that. So are we still doing okay so far in terms of understanding what is in W? All right. I don't see any questions. All right, cool, cool. All right, so now what we're going to do is to start to look into Zeta. Okay, so we're going to pick a specific rule in Zeta and kind of talk about it. So we're going to say, I'll try to pick something that's easier to understand first. So we're going to say, okay, this is going to be the easy one. All right, so dollar sign um, theta, theta, phi in a set. Okay, so this is our M, and then we have V dash to separate the left hand side from the right hand side. And this is something that we saw last week as well. So now we just have theta and phi. There we go. So this is a rule, and let me put parentheses around this entire thing, and then we'll say this is an element of the zeta that we are dealing with. So I'm confirming here, okay? I'm not really, asking whether it is an element or not. I'm actually confirming that this is actually an element of zeta, okay? So this is a confirmation, not a question. Are we still doing okay so far with, the rule that we have chosen to examine in this example? All right. Looks like there are not too many. There looks like there are no questions, but I'm gonna wait a little bit because I think sometimes it takes a little bit of time to formulate the question. Yes. So this entire thing is T. It is a single transformation rule of zeta because zeta is a set of transformation rules. So in this case, going back to the notation of the notes, okay, M in this case is the set of theta and phi. And in this case, we also have, let's see, WFF, right? So we have WFFQ. In this case, is going to be, oh, right, I need to give them parameters, okay, because I've been using parameters, so it's important to kind of maintain that. So we got theta, phi, and psi. So in this very specific example, it's just going to be the conjunction of the two. So in this case, it's really just theta and phi, like so. All right. Okay, so we got everything's up to this point. So are we still good? I mean, is everybody kind of still mapping the concepts like, WFFQ in this very specific example is just the conjunction between theta and phi? Because I'm trying to explain, which part is which part in the actual rule, and that's what I'm trying to do right now. All right, excellent. Okay, so now I'm going to have to start with iota because I cannot speak of anything else. I cannot speak of D without first starting with, okay, let's check out what is in iota because everything in iota is supposed to be in D also. So we'll go ahead and define what is now in iota. And it's going to be the same thing that we had earlier before. So 1 as a symbol is representing true, so 1 has to be in the set. Not false is also going to be there. And then we have P implies Q. Okay, so P implies Q. And then we have Q implies R. and this is basically the one that I had chosen to use as an example in the module itself. So I'm just repeating basically the same thing here. So in iota, other than 1 and not 0, the rest is really trying to model a certain quote-unquote reality that we want to apply rational logic reasoning to. Okay, so right now, P I think is text classes are boring. Q is people fall asleep when in a boring class, and then R is people feel refreshed after a class, after text class. So that's kind of what each letter is representing. And each letter, by the way, P, Q, and R, each letter is representing a variable, which means it is not set in stone. There's nothing here that says text classes are boring. It's a Boolean variable at this point, which means it can be true, it can be false. What is known to be true is if text classes are boring, then someone is going to fall asleep in text class. That is truth, okay? But there's no telling whether text classes are actually boring or not. What is also true in this case, given by iota, is if people fall asleep in the class, then they feel refreshed after a class. So those two are facts, okay? But whether text classes are boring or not is not necessarily true, because it is just P, which is a variable, because P is not mentioned here in iota. Neither is the negation of P. So we really do not know the value of P. All right. That is funny. All right. But are we okay so far, in terms of understanding what is iota doing here? Because it's the seed, okay? Everything in iota are automatically in D to begin with, everything that is derivable, okay? Because it takes zero derivation for 1 or true to be quote-unquote derived. So that's why, everything in iota are automatically in D. So is that okay? I'm going to state it here just to be sure. Okay, so I is a subset EQ of D. That is known to be true. It has to be the case. So are we still good so far? Kind of relating I and D, iota and D. Everything that is known to be true is derivable. That's kind of what it's saying. Maybe I should write it. Everything that is known to be true is quote-unquote derivable from everything that is known to be true. All right. There you go. Is that making any sense so far? All right. Okay. Very good. So now we can actually do something with what this thing is, right? So when we look at M, okay, we can say, M, let me see. Okay, let math tt wff, and this is a lot of typing on my side, but that's okay. Phi psi equal to well, it can match anything because there's no syntactic requirement. So theta is just, it can match anything in let me see, what am I saying here? This is just theta itself. Okay, so this is just theta. There we go. All right. So now we are using the, okay, let me refer back to the notes. So I'm going to go back and forth just a little bit here, but because it's necessary. So if I go back to here, now we're considering a single element of M, and we just so happens to consider the first item in the set of M. So back in the notes that I'm typing right here, I'm considering the first item, okay, which is looking at this as a WFF blah blah blah, okay, and I forgot the backslashes, and that's why you're seeing phi and psi without the Greek symbols. There we go, backslashes. All right, so are we still good? Why WFF theta phi psi is theta is one of the two things that we want to consider in M. And I am just going to specify a little bit more here. This is in M, in the M that we are talking about. Right, so those two thetas are not bound to each other. Well, it's going to be the same theta. So I am basically just saying, which well-formed formula are we considering at this point? So we are considering the well-formed formula, which can potentially use up to all three Greek letters to be just theta itself, without any operators nor the other two Greek letters. So is that okay so far? Because I want to show you guys, what A, B, and C I can choose to make this happen. Okay, it's just theta and not psi or phi. That is correct. It's just one because I am trying to say this. Look at this as WFF of theta, phi, and psi. Because you can always define a function where you have more parameters than you actually use. No one says you have to use all of the parameters. Your compiler may complain about it and go like, hey, didn't you forget these guys? You can say, no, I did not forget. I did not mean to use them. All right, so I'll let you guys process this a little bit before I move on. And by the way, there are about 2 more minutes before the road taking time is up, because I don't want anyone to complain to me and go like, but I was actually in class. I just kind of stepped away for 20 minutes, and now I cannot do my road taking activity. What's up with this? Are we good so far? Because I'm trying to relate back to the notes here, which is here to talk about, because I have to let you know which WFF we are talking about in M before I can instantiate that with A, B, and C in W that we have kind of talked about so far. Okay, so that makes sense. All right, so let me continue with this example. But before I move on, I'm going to have to put 2 additional items as elements of W, or at least confirm the membership of these 2, because it's going to be important. So I will say P is in W. Okay, I hope nobody is going to dispute this, because P, after all, is part of alpha and it's not one of the Greek letters. So obviously anything in alpha is already well formed. So that should not be a problem. And then I'm going to go like, well, same thing goes for Q and the same thing goes for R. Oops, wrong row on the keyboard, sorry. So there we go. Are we good so far with these 3 additional assertions that P is a well-formed formula, Q is a well-formed formula, and so is R as a well-formed formula? All right, so now it is also important to understand that I am not referring to membership in D. Okay, this is definitely going to be just W. I just need these things to be well formed. I don't need these things to be derivable by themselves. Okay, and the reason why I'm doing that is because in my choosing of A, B, and C later on, okay, so now I can say let lowercase a be P, and let lowercase b, just b equals to Q. And now we have one thing that really does not matter. Okay, so how I say, C is whatever, it doesn't really matter. Okay, we can pick whatever we want with C, as long as it is from W is fine. Okay, so we'll just say whatever. Okay, C is true. Okay, so I'm just choosing. Okay, so what I'm trying to do here is I am trying to explain in my notes here. So I'm trying to explain, what A, B, and C am I choosing as well-formed formulae in order to instantiate WFF of theta, phi, and psi. So that's what I'm trying to do right now. Actually, I take it back. uh, well, I didn't take. I'm not taking anything back because that is poor form. But I can expand. So I can say this one is this is also well formed, right? So nobody can argue about that one. And now I can also say that one is also well formed, right? So I'm just adding two more things. P implies Q is well formed. Q implies R is also well formed. Are we good so far? All right, cool. So now I can choose those two, as A and B. Okay, so I can choose A to be. Oh, I just need A. I don't even need the other two. So A can be P implies Q. Oops. There we go. Because B is not even used. Because remember, when you're defining this function as WFF, only the first parameter is actually used as a return value. The other two Greek letters were never referred to, which is fine. Okay, it's not a problem. All right. So now what are we going to do? Well, now we apply. Okay. Now we say, okay, I ask a question first. Okay, so I'm going to ask, what about math TTWFF? And this time I'm going to pass lowercase a, b, and c to that thing. And I'm asking, what about that? Okay. Well, first question is, do we know what is WFF representing? Yes, we know. Okay, this is how we kind of quote unquote define WFF, at least within this context. Okay. Next, do we know what is A, B, and C? Yes, I have chosen A as a variable to be P implies Q, which is from W. I have chosen B as Q, which is also in W, and I have chosen C to be true, which is also in W. So now I'm applying WFF. This is the definition of WFF. This is the actual application of WFF. You're calling the function, you're expanding, and ask, okay, what after the expansion, what do we get? So let's try to figure it out. Okay, so we have math TT. Now I haven't really mastered which side I should be looking at, because should I be looking at what you're looking at, or should I be looking at what I'm typing on the other side? So I think I should be looking at what I'm typing, because I found it if I don't, I'm not gonna type the right things. All right, so we have WFF ABC. And when you expand it, it really is just A by itself, right? Because we are ignoring the other two arguments completely. But what A really is in this case is just P implies Q. All right, so now I need to pause here and see if you guys can make all of the connections, because right now we are looking at what is WFF? Where is that coming from? Oh, it's just one of the elements of M. And where is M coming from? It is just the left-hand side of a transformation rule of an element in Zeta that we are looking at right now. So that explains WFF. What about A, B, and C? Well, that's just me choosing things in W. So I have just chosen A as a variable to be P implies Q, which is an element of W, because nobody complained about this when I said, okay, what about this as an element of W? Everybody seemed to say, okay, that seems pretty obvious. So I'm choosing B to be Q, which is also an element of W, because Q, after all, is just in alpha to begin with. And C is true, and true as a symbol is also in alpha. So I'll be making all of the connections until we get to this point here, and understand based on what WFF is, and based on how I have chosen A, B, and C, this is fine. I mean, by the time I'm done explaining all of this, I can probably write the code to actually work with a propositional system in JavaScript because that's actually already cooking in my head. It's like, oh, okay, I can do this, and then I can do that, and then I can do that. All right, so how does WFFQABC relate to WFFABC? Not yet. There's no relationship whatsoever. Okay, based on the rule that we have chosen to look at, this is how WFFQ is because we have chosen a rule where theta and phi is on the right hand side. So and WFFQ is here in this explanation here because I want a variable to specify. Okay, so if we just need to abstract the regular not okay, now I'm really mixing up my programming side and the explanation, the mathematical side. So WFFQ is a placeholder, is an abstraction of the result of what is considered derivable. But it is really just a well-formed formula, okay, with the placeholders being our Greek letters. Okay, we have theta, phi, and psi. So in this very specific case, we have chosen a relatively simple rule in Zeta, where it just says, okay, if you can find theta, for some thing that is already derivable, and you have found phi, which is also something that is already derivable, then the conjunction between those two things is going to be derivable. That's basically what WFFQ is representing, is ultimately what new derivable things have we found out in this case, in case the rule fires. And then the next question is, so how do we use this to prove other things? Well, we're going to get there. So right now I'm using a simpler rule, okay, but then later on we're going to use something that's more complicated. Okay, so just bear with me. We're going to have enough time today to use to explain what Elijah is putting into the text channel. So we'll get there. So we are finding A being P implies Q so that we can say theta is A, which is P implies Q. Eventually, not yet. Now we're working with individual components. All right? Okay, very good. All right, so now we're going to take a look at, because remember, we got two things in M, right? We got this thing here, and then we got this thing here in M. So now we have to say, what about the other one? Okay, so we have to work with the other one. And I'm going to have to change one thing, because I need B not to be just Q, but Q implies R. So I'm going to change that to Q implies R. So B is now changed to Q implies R, which is also a W, right? It is in W for sure because here we say because Q is in W, R is in W, and implication is it's an operator that has two operands. So when you have two values and you have an operator that requires two operands, then the resulting expression is going to be well formed. All right, so now we're going to expand the explanation to the following. Okay, so now okay, so I'm going to be super lazy here and just copy and paste. So we're going to reuse this, and this time we're going to say, forget about theta. This time we're just going to say, whatever phi is, return that. Okay. Now this is also another element of M, right? So basically WFF itself is a variable. It can bind to different things in M. So the first thing we bind in M is just theta itself, and which is matching this element of M. And then we say, what about the other guy? What about the other element of M? The other element of M is just phi by itself. So now we are binding WFF to just phi by itself. And then we look at this and go like, okay, what can we do with this? Okay, with the A, B, and C that we have chosen. So are we good so far? Does everybody understand that WFF really is a variable that binds to quote unquote a function? In C++, now I hate to throw this term out because it's going to confuse some people. WFF is a variable, and the type of WFF is a pointer to a function. Are we Are we more confused now than before, or are you guys going like, why didn't you say that earlier? If you just said that WFF is a pointer to a function, we would have understood it like right away, without all of these extra explanations. Okay, good. I think that's partially why the CISP430 being a prerequisite of a co-requisite of this class, which means CISP400 being a prerequisite implicitly, is really important because the concept of a pointer to a function is a level of abstraction, which is exactly what we're trying to do here. All right, so if that is the case, okay, then we ask, okay, what about, okay, remember WFF is now redefined because we have just bound it to a different element of M. So what if we apply this WFF to A, B, and C? Okay, it's the same kind of question like this one here, except WFF is no longer just returning the first argument, is returning the second argument now. In other words, it's just returning B, whatever B is. So given that, I'm just going to repeat, copy and paste, because this time it's just returning whatever B is. And B turns out in this case to be Q implies R, because that's how I have chosen. Yes, I did change it, but ultimately that's how I change. That's how I blah, 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 blah. That's how I have chosen B to be in this case. Are we still doing okay so far? Because what I'm trying to do is to explain the notations that I have put into here. So right now I have looked at every element of M, and we now have to confirm that if we have chosen A, B, and C the way that we had chosen, which are all elements of W, are the result of applying WFF to A, B, and C in each case, in each element of M, an element of not W this time. This has to be an element of D. So now we have to try to answer that question. But first of all, we are going to say, okay, so WFF is basically a transformation. If we apply that transformation to the way what we have chosen to be A, B, and C, which are elements of W, which basically all that says is A, B, and C have to be well formed. But once we apply WFF to those specific well-formed formulae, are those well-formed formulae elements of D? So now we have to answer that last question before we can fire the rule, because all of these things have to be true in order to fire the rule. So are we good so far? All right. So now I'm gonna expand the notes here. So now I ask the question. Okay, so now we want to ask P implies Q in D. Okay, and I'm gonna put a question mark here. Okay, so I'm trying to have you guys to help me figure this out. And obviously my LaTeX expression is off a little bit here. I meant to use a close parenthesis and then I typed a $sign, but there we go. So what is the answer to that question? Because we need to make sure that after applying WFF, which in this case is just saying, just return the first parameter. Yep, okay, so we say yes, okay. And now we ask the other question, okay, which is what about Q implies R? Now we have to ask, is that in D? Well, the answer is yes, it is also in D because P implies Q and also Q implies R. They are both in iota to begin with. Everything in iota is automatically in D, and that's why these two are also in D. Exactly, so what Danny typed in the channel is correct. Alright, so are we still doing okay so far? Does everybody understand why now I have to ask these two questions? Because before I was only concerned about, are A, B, and C in W. But suddenly, because I have to evaluate the expression inside the parentheses here, now I have to ask, once we apply the WFF template to the well-formed formulae that I have chosen from W, is the result of that derivable? And that is why now we have to shift our attention to whether these two items are in D, which means are they derivable or not. Alright, so now that we know that they are also derivable, then guess what? We have just met the requirement of this specific universally quantified expression. This entire thing is now known to be true. So I'm going to pause here a little bit because I really want you guys to let all of that stuff to sink in and then understand why now I say, oh, now we have met all of the requirements. We have chosen A, B, and C in W, which means they are well formed. I chose one element of Zeta, being the kind of more or less trivial transformation that I have chosen here. I break up the transformation into two parts. The first part is a set of well-formed formulae. The second part is also a well-formed formula using the Greek letters. And then I look at every single element of the set, which is the first item of a transformation rule, and I ask, if I instantiate each one of these things, which is basically a structure with some placeholders. So instead of the placeholders, if I just kind of stuff in, the three well-formed formulae that I have chosen in W, once I stuff it in and expand it, is the expanded expression in D? And the answer is yes. Okay, so we have already shown step by step that we have met the requirement of the universally quantified expression. Alright, so that's my explanation, but I want to make sure this sinks in before we quote-unquote fire the rule, to basically say, okay, so what is the big deal here? Okay, once we have met all the requirements, what does it mean when we fire the rule? But I do want to make sure that we got everything done first, everything explained and understood for the conditional part of this rule. Alright, so the question is, so we need to establish that T is in, no, T is not in D. T is from Zeta. T is a transformation rule. It is in Zeta. A, B, and C need to be in W, but after transformation, after we apply each element of M to what we have chosen as A, B, and C, the resulting expression needs to be in D. So there are a few levels of, I wouldn't say abstraction, but these things come from a few different places. And the next example may actually help you guys understand it too, because I'm going to use a different rule and use the same approach. So this way, when you guys compare the two examples, you will understand, okay, certain parts are different because I have chosen a different rule, but certain parts are the same because the way we apply the rule is exactly the same way. Yep. Yes. So we conclude with that. Then it is correct. So let me switch back to the note that I'm typing here. Okay. So now that the condition of the rule is satisfied, then we quote-unquote fire the rule and confirm that. Okay, so I'm going to make it very clear here. Okay, so I'm going to use math TT WFF underscore Q, and we have A, B, and C. Now remember, A, B, and C are really not variables anymore. We have chosen what is A, what is B, and what is C. A is P implies Q, B is Q implies R, and C is true. Okay, so once we apply that, and we know what is WFFQ, WFFQ is really just the right hand side of the rule, and the way we defined it is all the way over here. So now we basically say, once you expand it based on what is A and what is B, So we first here say this is just A and B. But once we know what is A and what is B, now we can say, oh, this means we have P implies Q and Q implies R. So now we have said that this thing is derivable. We have now confirmed that this is now derivable. Alright, so I'm going to let you guys read this a little bit, and then I'll set up the next example, and I think that will basically use up, well, maybe not. The next example is going to be a little bit shorter because now that we have introduced the method and what these symbols and steps are representing, I think the next one is going to be a little bit faster. But I'm just going to pause here, make sure that we don't have any questions before proceeding to the next example. All right. So is subscript q kind of a marker? Yeah, it's because otherwise, we cannot, because WFF by itself is a variable that's a pointer to a function. WFFQ is just quote unquote another local variable that has a type of a pointer to a function, but it points to something that's different. Because the way we use for all, okay, so let me go back here. So the way we use this for all here, that's basically a mini loop, okay? Because so the loop variable in this case is using WFF, but WFFQ is you can look at this as a local variable of a quote unquote higher scope, because WFFQ has to do with T, and then WFF has to do with M, or how we confirm that once we apply A, B, and C as arguments to theta, phi, and psi, every single element of M is going to say, yep, that thing is in D. So they're both local variables, but WFF is a local variable just to the loop to confirm every item in M. When you apply A, B, and C, when it is applied to A, B, and C, the resulting expression is derivable. So WFF is for that purpose, and then WFFQ is for designating what is the right-hand side of the transformation rule, so that we can say, okay, now we can refer to WFFQ and just apply that expression, but with the arguments of A, B, and C the way we have chosen A, B, and C in W, and then the result of that application, the resulting expression of that application, is now confirmed to be derivable. So I'm hoping this is helping to answer Luke's question. It's kind of a variable, but the cube makes it different, right? So the only reason why it has a subscript of q here is so that so that people are not going to confuse WFFQ with this WFF with no subscript here. It's just a name, that's all. We have two different variables, and I just want to make sure that we don't use the same name for both variables. Are we good so far, or is there any explanation that we need to do here before we take a look at the next example that Elijah was suggesting earlier? All right. I'm not seeing any questions one way or another. I am going to move forward then. So if you guys have any questions, after today's class, you can go ahead and just ping me in the text channel, or using the, specifically use the questions, text channel. That would be even better. That's what it's for. All right. So now we're going to take a look at another example. So I'm going to say, well, it's going to use the same premise here. So it's going to be another example, but I'm going to reuse a portion of this. I can reuse everything all the way up to the specific rule that we have chosen. So I am just gonna okay transformation rule 1. Okay, so now I can right shift everything here all the way to the end. Let's see, 17 to 32, right shift. Nope, doesn't like that. 17 to 32, right shift. And it right shift too much. Ah, okay. Oh, that's because the shift width is set incorrectly. So let me try that one more time. Oh. All right, there we go. Just shift once. Whew, okay. My VI is rusty. All right, so now we're going to look at another transformation rule. So we'll say this is transformation rule 2. And now we're going to take a look at the transformation rule itself. All right. Oh, we do need one more level of indentation here. All right, so this one is going to be a little bit more involved because the first expression in the set is theta, oops, right arrow phi. So now we have a slightly more complicated well-formed formula as the first element of the rule, and the second one is going to be more complicated as well. So the second one is going to be phi implies psi. There we go. And then the resulting expression is going to be a little bit more interesting because it's going to refer to theta and psi only. It does not refer to phi, and it's not going to be ended. It's going to be implied. There we go. So this is another rule that we have just handpicked from Zeta. Okay, it's representing a meaningful Boolean algebra step that we can perform when we have implications. All right. So are we doing okay so far with the rule itself? Okay. We have two templates to satisfy on the left hand side, and then if these are satisfied, then the resulting expression only refers to theta, which is the first item, the left hand side of the first implication, and psi, which is the second item or the right hand side of the second pattern that we have to match. Are we good so far? All right. So now I have to select my A, B, and C, right? So I'm going to say, I'm selecting my A to be P. I'm selecting my B to be Q, and I'm selecting my C to be R. So this time it is quite important that all three, have meaningful members from W. Okay, so now it is important to understand that A, B, and C, they're all representing something from only W, not D. Okay, because P by itself is not derivable, PQ by itself is not derivable, and R by itself is also not derivable. They do not need to be derivable. So the first thing we do is we take a look at the first element of M, which is this expression here. Okay, so we're going to look at that expression. So we're going to say let math TTWFF theta THETA phi psi. So this time it is going to be a little bit more complicated because it's going to be theta implies phi. All right. So this is the definition of WFF, at least for the time being. So now we want to consider all right, so I'm just gonna stop here, not stop the lecture, but stop the notation here. Just so we are now applying, okay? Given that WFF is defined as theta implies phi, when theta, phi, psi are the parameters, now we are saying, okay, what if I have chosen A as P, B as Q, C as R, and I'm going to apply. I'm going to call the function right now. So after calling the function, I'm just gonna shortcut this a little bit. So we end up with something that looks like this, right? So we just say, oh, okay. So all that becomes is just P implies Q. So I have a typo here, right? Okay. Are we good so far? Yeah. Based on how I have chosen the values A, B, and C, and apply what WFF is representing right now, then I end up with P implies Q. Okay, very good. So I can now basically just repeat these two, except this time we apply it to the other the other element of M, which in this case is phi implies psi. So I am now binding WFF to the second element, which is phi implies psi. So theta is not even referred here. Okay, you can say whatever going to theta is fine, but based on how we have chosen A, B, and C, so you cannot change the way you choose A, B, and C when you're evaluating different elements of M. Okay, once you have chosen A, B, and C, they are stuck. Okay, you basically you have to use the same set, the same binding of A, B, and C throughout the universally quantified expression. So based on that, okay, so now we have Q implies R, like so. Okay. So now the question is, okay, after we choose what is A, B, and C, after we apply WFF, where WFF is really just an element of M, is the result an element of D? So the answer is yep, in both cases. So this is in D because it is part of the iota set, right? So this is also in D because that is also part of iota. Are we doing okay so far? This is kind of like shorthanded compared to the one before, but it's really the same process. So once I have confirmation this is okay, then we will go ahead and fire the rule, because what this is indicating up to this point is I have just met all the requirements in order to fire the rule. Okay, very good. Okay, so we are all good here. So now we can say fire the rule. So when we fire the rule, all we are doing is to say, okay, given what we have chosen as A, B, and C, now apply those as arguments, but not to any element of M, but we want to apply those to the right-hand side of the transformation rule, which we term it as WFFQ. So in this case, WFFQ is this part here. This is our WFFQ. So it is probably helpful for me to kind of make a notation of that first, and then we'll refer to it. So in this case, math, TT WFF underscore Q of theta, phi, and psi is theta, implies psi. Okay. And this is here really just so that, it's double arrow, so I need an uppercase R instead of a lowercase r. There we go. Alright, so this definition here is really just to remind ourselves, what is the right-hand side of the transformation rule, because we assigned a term to that side and we say, okay, let's just look at that thing as WFFQ. So this is how WFFQ is defined. So once we have defined WFFQ, then we fire the rule. So when we fire the rule, then we basically just apply WFFQ but this time not to the Greek letters. Remember, the Greek letters are only useful to serve as names of parameters. Now we have to give it actual values to process. So we have chosen A, B, and C, right? So those are the values that it's supposed to work on. And after after a few steps, this is what we're going to end up with, which is P implies R. And we are confirming that P implies R is derivable. So let me go back and add a little bit more here, okay? Confirm that. There we go. So are we good so far? Once we fire the rule, we are basically just looking at the right-hand side of the rule and say, okay, apply this template to the values that we have chosen as A, B, and C, and then the resulting well-formed formula is going to be considered derivable. So we are basically just adding more and more stuff to be derivable as we apply these rules. So are we good so far? Okay, I did go over time a little bit. Not by too much, just 2 minutes. All right. So I am done with today's lecture. Basically today's lecture is focusing on a very small but important portion of propositional calculus, because what I have talked about today is the mechanism of how each rule is going to be applied and how everything ties in. In other words, today's lecture in a way is extremely important because it is not just talking about, oh, this is iota and this is omega, this is zeta, and so on and so forth. It is tying in all of the concepts and say, okay, with all of these things, what do we do with these things? Okay, that's today's lecture. It's basically me, without writing code in JavaScript, telling you how it is supposed to work, the mechanism by which this works. So, all right. So looks like most people are getting something out of today's lecture. I will give you the notes, okay? Because it's not. I mean, giving you the notes is not going to help a lot, because ultimately you kind of have to understand what it is representing, right? So I'm just going to give you the notes in the text channel as an attachment. Let me save it first. Yep. Okay. So now I can attach it. And let's see, where is it? 2022, today is the 7th. So I am giving you the markdown file. You can download your own tool. You can just you can go to any webs. There are plenty of websites that can turn an MD or markdown file into PDF. Okay, so you can easily turn it into whatever format you want to turn it into. But for those of you who want to add your own notes, okay, you can also use Markdown and further explain all of these steps and clarify what is what, why is this step important, what is the significance of this symbol, and so on. All right, so we got a question in the text channel. So in that case, you probably want to differentiate between the two WFFs. So you might want to use a subscript 1 for the first one and the subscript 2 for the second one. Because otherwise, you're basically saying they're identical. They're basically the same formula, in the set. All right. All right, so I think we are good for today. All right, so there's a question about what is v dash in the file. V dash is what is producing the infer symbol, which is the one right here. So this is called v dash when you type it out in LaTeX, and Markdown is just borrowing LaTeX when it comes to math equations. Yep. Yep. Okay, so with Luke's latest text message, so now we have WFF1 and WFF2 and then WFFQ. So that's all good, except we also have to remember WFF1, WFF2, and WFFQ. They're really just placeholders. They are pointer to functions. So right now we don't really know what function they're pointing to. We are basically just saying, okay, we have one pointer to a function called WFF1. We have another pointer to a function called WFF2, and then we have another pointer to a function called WFFQ. But we don't know what functions they're actually pointing to, and as a result, there's no way to actually use whatever is in the text channel right now to make a match of what currently in D can we apply these things to in order to end up with a new formula that is also known as derivable. So it needs to be more specific in order to be utilized. But as an abstraction, that's okay. Right. Okay. So that would be okay as the prototype, but not the implementation. Yes. But so depending on the transformation rule, sometimes you only have one element in the set, sometimes you have two, and other times you have none. Remember the one that has an empty set as M that we looked at last week? So that one is kind of funny because it doesn't matter what you specify as A, B, and C, it all goes, right? Because there's no requirement of anything needs to be in D to begin with. You just have to give me something that is well formed, and I'll give you something that should be derivable as a result. So that's an interesting one. Not necessarily a really useful one, but interesting. And I believe we talked about that one on last Wednesday. All right. So if you guys are ready to go, I will basically just kind of get off of the channel, but I will still kind of keep an eye on the text channel for a while, just to make sure that all the concepts are clear before we hand off to I hand off you guys to do something else. Okay, there we go. So I'm gonna get off the voice channel because it doesn't seem like there are any additional questions to answer here. And also